Dante Certification Program Level 3. In this module, we will look at bandwidth utilization. Dante is carried on an IP network. Consider this TCP/IP model again. At the application layer, we have the requirement for enough transmit and receive flows. At the transport layer, we need enough ports for these flows to map to. At the internet layer, we need enough IP addresses for our devices. At the network access layer, we need to make sure we have enough bandwidth to carry all of the above. Now that we have identified resource requirements for a Dante network, let's look at how the subscription process works in Dante. You plug a laptop into the switch. Then you plug a microphone into the switch. The microphone announces itself. Dante controller hears this announcement and populates its routing page. Now you plug a speaker into the switch. The speaker announces itself. Dante controller hears this announcement and populates the routing page. Then you decide to subscribe Paul to Bob. Dante controller tells Paul to ask Bob for channel 1. Paul asks Bob for channel 1 at its latency setting. Bob checks if that latency setting is equal to or greater than its own setting. If this is true, the flow is created with Paul's latency. If not, the flow is created with Bob's latency. 6 megabits per second bandwidth is used between Bob and Paul. 0 megabits per second bandwidth is used on the cable between the switch and the computer. Now, Paul reports good subscription. Controller updates this record with a green check mark. This is what happens behind the scenes every time you create a subscription in Dante controller. Next, let's see how bandwidth is utilized in a Dante network. Picture this scenario. Pay careful attention to all the bandwidth usage indicators in this example. Device A sends a signal to device B. Device C sends a signal to device B. Device B then sends a signal to device D, and device B sends a signal to device E. Now we decide to expand this network and add an internet connection. We stream Netflix from the internet. Then we send audio from Netflix to device B using DVS, that's Dante Virtual Sound Card. So let's look at a different example involving more devices. Here we have 14 devices, 64 channels each, with 32 flows for each device. The maximum unicast bandwidth per node in this case is 122 megabits per second. That gives us more than a gigabit. Maximum receive bandwidth per node is still 192 megabits per second unicast, which means we will run out of flows. Minimum backplane bandwidth of the switch is 28 gigabits per second. The worst flow structure possible would be 32 by 2 channel flows on a device. In this case, only a two-way split is achievable in unicast. Dante is unicast by default for good reason. In unicast, bandwidth is only used between a receiver and a transmitter when an active subscription is made, and on the shortest path between the receiver and the transmitter. When a multicast flow is created, it doesn't care about a receiver. Even if there's no subscriber, it still uses bandwidth everywhere. Dante cannot dynamically switch unicast to multicast. Now, let's see what happens when we turn on IGMP. Think of the previous example where we ran out of bandwidth. If all devices are set to full multicast, the switch would still be fine, but devices would not. 8 by 12 megabits per second multicast flow gives us 1.344 gigabits per second. This is more than a switch can handle, but it's still 4.8% of the backplane bandwidth. Sending 832 channels into a network where they flood and the maximum receive possible is 64 channels seems like a huge problem. Remember, with IGMP snooping off and everything multicasting, we were trying to push 1.344 gigabits per second down each gigabit cable. Now, this is obviously not going to work. We turn on IGMP snooping. Each device can only subscribe to 32 flows. This is a maximum bandwidth of 384 megabits per second per port. The backplane bandwidth is unchanged at about 4.8% capacity. This is why multicast management is always a priority over QoS. Assume all 14 devices on the top switch are transmitting on a 1-to-1 mapping to the 14 devices on the bottom switch. This gives us 896 channels. With 16 flows per device at 6 megabits per second, we get 1344 megabits per second. Simply put, the bandwidth has ran out. So, what's the solution? 10 gigabit link. That solves the problem. All of these devices are transmitting at a constant data rate. Remember, QoS will do nothing here. It's not the solution.